In June 1972, technicians at France's Commissariat à l'Énergie Atomique, also known as CEA, were reviewing uranium ore samples imported from a mine in Oklo, Gabon, a former French colony turned independent state in West Africa. What they found was bizarre. The uranium was missing something critical. Specifically, it had significantly less uranium-235 than expected, about 0.717% instead of the natural 0.720%. That might sound minor, but in nuclear physics, such deviations aren't small, they're alarming. Uranium-235 is the isotope responsible for sustaining nuclear fission. It's rare, radioactive, and unstable. It also decays faster than uranium-238. It's more abundant but less fissile sibling. In natural uranium, the U-235 content remains almost constant over human timescales due to this imbalance. So why was Oklo's ore subtly but consistently depleted? Initial suspicion fell on contamination or enrichment irregularities, but repeated tests confirmed the readings. Not just in one shipment, but across multiple samples from different reactor zones in the mine. The anomaly held. And then the smoking gun appeared. Isotope signatures of several rare elements, neodymium and ruthenium, among them, revealed telltale fingerprints. Their isotopic ratios mirrored what you'd expect from a reactor that had been running, not a hypothetical one. A real, active reactor. But here's the twist. Oklo had never seen industrial development, let alone a reactor. The geological layers containing the uranium dated to 2 billion years ago. In a groundbreaking paper published in Nature by Bouzigues and colleagues in 1975, French physicist Francis Perrin and his team proposed the unthinkable. The Oklo uranium deposit has sustained a natural chain reaction, what we now call a natural fission reactor. They weren't being metaphorical. They meant literal nuclear fission, just like in modern reactors, had occurred underground for up to 300,000 years in episodic pulses. Subsequent studies confirmed this over and over. The neutron capture profiles for certain isotopes, particularly samarium-149 and xenon-135, matched those generated by artificial reactors. In fact, some fission products had migrated only millimeters in 2 billion years. That suggested the reaction wasn't just real. It had been thermally regulated and geochemically stable over geological time. A 2004 review published in Physics Today by Alex Mashik summarized the consensus. This was a naturally occurring nuclear reactor, and the implications were immense. Not only for our understanding of nuclear chemistry, but for how we model deep time. No lab, no design. No species capable of building anything remotely close to it, just geology, hydrogen atoms, and an incredibly precise sequence of coincidences. This wasn't just unexpected. It was supposed to be impossible. The confirmation came in stages, but the implications dropped all at once. If the isotopic patterns in Oklo's uranium ore weren't caused by human activity and couldn't be explained by contamination, then there was only one conclusion left. A sustained fission chain reaction had occurred, naturally, in the distant past. That meant conditions for nuclear power, once thought uniquely engineered, had spontaneously arisen in nature. Fission, in essence, requires three things: a sufficient concentration of fissile material, like uranium-235, a moderator to slow neutrons, typically water, and a configuration that maintains critical mass. By all logic, that shouldn't exist naturally, but 2 billion years ago, it did. Back then, the isotopic composition of natural uranium was different. Due to its faster half-life, uranium-235 made up about 3.1% of total uranium content, exactly the same enrichment level used in modern commercial nuclear reactors. That number wasn't just close, it was reactor grade. The natural decay of U-235 had not yet brought it down to the inert 0.7% we see today. This idea was initially greeted with skepticism, but once scientists ran neutron flux simulations on the uranium seam geometry, it became clear. The ore deposit's shape, porosity, and water permeability all contributed to maintaining criticality. When groundwater infiltrated the uranium-rich zones, it acted as a neutron moderator, slowing down fast neutrons so they could trigger more fission events. As the reaction heated up, the water boiled off, removing the moderator and shutting down the chain reaction. When the rock cooled, water seeped back in and the process started anew. A 2006 study in Geochimica et Cosmichimica Acta by Hidaka and Hollinger used isotopic analyses of neodymium and molybdenum to reconstruct the neutron economy of the site. Their findings? The reactor ran intermittently in cycles about 30 minutes on, 2 hours off, like a heartbeat buried in stone. In total, 17 separate natural reactor zones have been identified at the Oklo site. Each one represents a separate fission core that came online under its own geological configuration. Collectively, they are estimated to have produced the equivalent of 100 kilowatts of thermal power for hundreds of thousands of years. That's not a blip. That's a deep-time power plant. No machines, no minds. Just chemistry and physics doing what they do best. The Oklo reactors weren't a metaphor. They were real, self-regulating, long-lasting, invisible to the surface world for 2 billion years, until a French shipping manifest cracked open the mystery. To appreciate how the Oklo natural reactor came to exist, we need to understand just how finely tuned the conditions had to be. This wasn't just a freak accident. It was a rare alignment of physical constraints, planetary chemistry, and geological structure, each one a prerequisite, non-guaranteed. First, the fissile fuel. Today, natural uranium contains only about 0.72% uranium-235. That's too low to sustain a chain reaction under natural conditions. But uranium-235 decays faster than its sibling uranium-238. 2 billion years ago, when the Oklo reactor formed, the U-235 fraction stood at about 3.1%, a concentration nearly identical to the low-enriched uranium used in commercial nuclear reactors. This was predicted by nuclear decay models and confirmed in a 1989 Science article by Cowan, who showed that this enrichment would only have been possible during a narrow window of time between about 2.5 and 1.5 billion years ago. Second, moderation. A nuclear chain reaction needs a way to slow neutrons down. Fast neutrons tend to pass through uranium without triggering fission. In man-made reactors, water serves as the neutron moderator. At Oklo, the same applied. The uranium ore was located in porous sandstone laced with ancient groundwater. The water flowed through the seams, absorbing heat and moderating neutron speeds, allowing the chain reaction to sustain itself. But moderation alone wasn't enough. For the system to persist over geologic time, it had to be stable. Here, the geology helped once again. As the fission reaction heated up, it boiled away the water, removing the moderator and shutting the system down. Then the rock cooled. Water returned and the reaction restarted. This created a negative feedback loop, nature's own reactor control system. These cycles likely occurred over hundreds of thousands of years. Studies published in Earth and Planetary Science Letters by Nagy and colleagues in 2001 suggest that the reactors could have operated for up to 850,000 years. During that time, they produced an estimated 15,000 megawatt days of thermal energy. That's enough to power either 12 million people for a day or roughly 33,000 people for a year, the equivalent of a small city. The reactions were also remarkably efficient. Fission products like samarium-149, which readily captures neutrons, were found in depleted states, proving neutron flux had been sustained over long periods. Their distribution was at random. It tracked spatially with zones of previous criticality. Isotopic analyses of xenon gas trapped in the rock further confirmed these neutron densities, with xenon-136 showing depletion patterns matching reactor behavior. Even the geometry mattered. The uranium-rich seams were flat and wide, allowing fission-generated neutrons to stay within reach of fresh fuel. Too thin, and the neutrons would have escaped. Too thick, and the heat wouldn't have dissipated. Oklo's rock formations hit the Goldilocks zone, just right. In a 1996 review for American Journal of Science, Robert G. Alexander called Oklo a precise large-scale slow-motion physics experiment set up by Earth itself. That's not hyperbole. Nature had, against all odds, constructed a reactor indistinguishable in principle from the ones engineered at Oak Ridge or Chernobyl. Except this one ran cleanly for 1 million years, and nobody noticed until it was over. That's the science. No mysticism, no magic. Just uranium, water, and deep time. The Oklo natural reactor functioned with the kind of stability and feedback that even modern engineers admire. But this was no miracle. It was a product of special hydraulical and geochemical conditions that created a self-regulating system capable of sustaining controlled nuclear fission across millennia. Once uranium-235 concentrations reached reactor-grade levels, about 3.1%, the key was moderation. At Oklo, ancient rainwater slowly percolated through sandstone aquifers into uranium-rich seams. The water didn't just cool the rock, it acted as a neutron moderator. Slower neutrons have a higher probability of triggering additional fission in U-235 atoms, enabling a chain reaction to occur. But chain reactions can quickly become runaway events unless controlled. Here's where the system's brilliance becomes apparent. As fission proceeded, the local temperature rose. This heat caused the groundwater to evaporate, driving it out of the reactor zone. With the water gone, neutron moderation ceased and the reaction shut down. The rock then cooled. Water seeped back in. The cycle restarted. In a 1990 study published in Nature, scientists led by Georges L. Reynolds used isotopic profiles to reconstruct the thermal cycling of the system. Their models suggested a regular oscillation, around 30 minutes of active fission followed by a cooling phase lasting up to 2.5 hours. The reactor effectively pulsed on and off in a pattern governed by the movement of water and heat through fractured rock. Further support came from xenon isotopes trapped in aluminum phosphate minerals. A 2004 paper in Nature by Alex Meshik and colleagues reported that xenon-136 and xenon-134 concentrations in the minerals showed ratios characteristic of sustained neutron flux. The diffusion of these gases in the rock, normally impossible to date, was frozen at the time the reactor shut down. These gas pockets became tiny nuclear clocks, preserving the memory of ancient reactions with extraordinary precision. The reactor zones were also spatially distinct. 17 have been identified so far, each operating in slightly different geochemical contexts. Some ran hotter, some longer. All showed consistent depletion in uranium-235 and the accumulation of fission byproducts like neodymium-134, cerium-140, and samarium-147. Fission yields suggest a total energy output of roughly 15,000 megawatt days, equivalent to burning over 100,000 metric tons of coal. But this energy was not released in cataclysm. It was spread across time and space, diffused in cycles so stable that no explosive event ever occurred. The Oklo reactor wasn't a meltdown, it was a whisper, a natural process humming along for hundreds of thousands of years. When the conditions were right, it ran. When they weren't, it slept. No control rods, no turbines, just a slow nuclear rhythm etched into the stone. The Oklo phenomenon wasn't just rare, it was time-locked. A perfect storm of nuclear physics and planetary evolution that could only occur in Earth's deep past. Today, even with similar rock formations, such a reactor couldn't form naturally. The physics no longer works. The main reason lies in uranium's changing isotopic composition. Uranium-235, the isotope responsible for sustaining fission, has a half-life of about 704 million years. That means it decays significantly faster than uranium-238, which has a half-life of 4.47 billion years. As a result, the proportion of U-235 in natural uranium has been declining ever since the Earth formed. 2 billion years ago, during the Paleo-Proterozoic era, the natural ratio of U-235 to U-238 was around 3.1%, a critical threshold. Below that, a natural reactor struggles to maintain a chain reaction, even with water acting as a neutron moderator. Today, the ratio is only about 0.72%. That's too low to sustain fission without artificial enrichment. This decay curve was precisely calculated in a 1976 paper by Kuroda in Proceedings of the National Academy of Sciences. He showed that there was a narrow window, roughly between 2.5 and 1.5 billion years ago, when the natural uranium ore had just the right concentration of U-235 to make fission possible under natural conditions. Oklo fell squarely within that window. Miss it, and the reactor never happens. But enrichment wasn't the only requirement. The geological architecture had to cooperate too. Oklo's uranium-rich seams were formed by hydrothermal processes that concentrated ore into permeable sandstone layers, allowing groundwater to flow and act as a moderator. Without both the right enrichment and the right hydrogeology, the system fails. Modern uranium deposits lack this combination, In fact, Oklo is unique not only in its timing, but in its structure. The site's sedimentary basins, known as the Franceville Basin, developed under a shallow marine environment with abundant organic material which helped bind uranium into dense concentrated ore bodies. Moreover, today's groundwater chemistry is different. Increased oxygenation of the Earth's surface since the Great Oxidation Event changed how uranium behaves in solution. 2 billion years ago, uranium was more mobile, more likely to collect into high-grade ore zones, and more responsive to redox gradients created by microbial activity. A 2008 study in chemical geology by D'Asbach and colleagues confirmed that these ancient biochemical conditions were essential for forming the type of ore bodies that made Oklo possible. Finally, tectonic stability played a role. Despite multiple orogenies, mountain building events, and shifts in Africa's continental crust, the Franceville region remained stable enough over billions of years to preserve the isotopic evidence in situ. The reactor zone stayed sealed, unshaken, and unbreached. All of this means the Oklo reactor wasn't just unlikely, it was time-bound, a one-shot event in Earth's nuclear history. If you were to replicate the same geological structure today, even in the same place, it wouldn't work. The uranium's no longer hot enough. The clock has run out. The window's closed. What surprised scientists wasn't just that Oklo worked, it's that it contained itself. For hundreds of thousands of years, radioactive fission products, some of them with half-lives of millions of years, stayed more or less where they were created. In modern terms, Oklo functioned as a natural analog for deep geological nuclear waste storage, offering a rare real-world case study that spans geological time. Among the fission products studied were isotopes of neodymium, ruthenium, and cesium, and technetium. These are the same highly radioactive materials that accumulate as waste in man-made reactors. Normally, scientists rely on productive models to simulate how such isotopes might behave underground over millennia. But at Oklo, those models could finally be tested against reality. The containment was remarkable. In a seminal 1992 study published in Nature, scientists showed that elements like neodymium and samarium had migrated no more than a few centimeters from their point of origin, even after 2 billion years of exposure to heat, radiation, and water percolation. That kind of mobility wasn't just surprising, it was paradigm shifting. Especially significant was the behavior of radioactive xenon and krypton, gaseous fission products that would normally escape from a nuclear core. At Oklo, they were found trapped in tiny mineral inclusions, often in the mineral aluminum phosphate. A 2004 paper in Nature by Meshik and colleagues detailed how these gases were preserved in place, providing not only evidence of sustained chain reactions, but a geological record of gas containment lasting geological epochs. Even the more mobile isotopes like cesium-137 and strontium-90 showed unexpectedly low levels of dispersion. A 2005 report by the IAEA used Oklo data to argue that the right combination of clay, phosphate minerals, and reducing conditions, low oxygen environments, can effectively immobilize radionuclides over millions of years. This has had a real-world impact. Oklo became a model for future nuclear waste storage facilities, like the Oklo repository in Finland or the waste isolation pilot plant in New Mexico. These modern sites aim to replicate the isolation and geochemical stability that Oklo naturally achieved. Its record shows that under the right conditions, radioactive waste can be locked away safely for time spans far longer than human civilization has existed. In fact, Oklo did more than reassure scientists. It validated their designs. It demonstrated that nuclear products don't have to leak, leach, or poison groundwater. They can stay buried, if the geology is right. And now, we know exactly what right looks like, because the planet already did it once. As soon as news of Oklo's natural nuclear reactor went public in the 1970s, it was only a matter of time before it escaped the confines of geophysics and entered the realm of pseudoscience. To the scientific community, Oklo was an incredible case of nature mimicking technology. To conspiracy theorists, it was proof of something far more dramatic, often absurdly so. Some claimed Oklo was a remnant of a prehistoric civilization with advanced nuclear technology, wiped out by their own atomic experiments. Others suggest it was evidence of ancient extraterrestrial intervention, with the uranium mine serving as a decommissioned alien power plant. The ancient aliens crowd cited the perfect ratios and long-lasting regulation of the reactor as signs that it couldn't have happened naturally. The internet helped these ideas go viral. The science, as always, traveled slower. In reality, the mechanisms at Oklo have been studied in more detail than most artificial reactors. Dozens of peer-reviewed papers have reconstructed its isotope signatures, neutron flux profiles, and thermal behavior. The reactor's lifespan, output, and even self-regulation cycle are supported by precise, testable physical models. Every chemical signature has a terrestrial replicable explanation. For example, fission byproducts like samarium-149 and xenon-136 were found in ratios identical to those produced in modern fission reactors. That's not mysterious. That's what nuclear fission does. The geometry of the uranium deposits, the porosity of the rock, the flow of groundwater, none of these require intelligence to explain, just physics, just chemistry, just deep time. This didn't stop outlets and authors from spinning the site into speculative fiction. It appeared in fringe documentaries, conspiracy forums, and even made its way into pop culture lore as nuclear anomaly too perfect to be natural. But that interpretation misses what's truly remarkable about Oklo, because the real story is more astonishing than the myths. It shows that Earth without any guidance was once capable of assembling all the ingredients for a sustainable nuclear reaction. No gods, no aliens, no engineers. Just the right elements in the right place, at the right time. And that's the deeper awe. Not that someone built a reactor, but that no one had to. Oklo forces us to reframe our assumptions, not just about geology or nuclear science, but about the boundary between the natural and the artificial. We often treat technology as something uniquely human, clever, deliberate, and engineered. But Oklo reminds us that the universe plays by its own rules, and sometimes those rules converge on systems that look like machines, even when no one is there to build them. This natural reactor didn't just flicker on and off, it self-regulated. It managed thermal feedback, neutron moderation, fuel density, and waste containment. These are the very challenges faced by nuclear engineers today. And yet 2 billion years ago, they were solved organically by pressure, chemistry, and mineral flow in the Earth's crust. The scale of time involved is staggering. Oklo began operating when Earth's biosphere was still dominated by microbial life. There were no plants, no animals, no continents as we know them. Oxygen was just starting to accumulate in the atmosphere, and yet beneath the ground, something was happening. An experiment in physics humming away undetected for hundreds of millennia. And when it ended, when the U-235 finally dipped below critical mass or the groundwater shifted, it left no cataclysm, just a silent archive. The signatures remained trapped in rock, awaiting rediscovery by a species that wouldn't exist for nearly 2 billion more years. In 1972, that species finally noticed. What Oklo teaches us ultimately is humility. The universe doesn't wait for intelligence to create complexity. It doesn't need blueprints or intentions. It needs only time, energy, and the freedom to explore every possible arrangement of matter. Some of those arrangements will look like chaos. Others, like a self-regulating nuclear reactor, will look like intention. But they're all part of the same logic. A logic that doesn't begin with us and won't end with us either. We like to believe technology defines us. But in Oklo, Earth built a reactor before we built fire pits. And in doing so, it left behind a quiet reminder. Nature got there first. So what does it mean that 2 billion years ago, this planet quietly built a nuclear reactor in the dark? It means intelligence isn't the only way to produce complexity. It means that time, deep, patient time, can create systems that rival our best designs. And it means we're not the first to run experiments on this world. We're just the first to notice. Oklo doesn't tell a story about lost civilizations or forgotten gods. It tells a story about the raw potential hidden in matter, chemistry, and chance. A story that took 2 billion years to whisper its way into our equations. And now we get to listen. If this video shifted the way you see Earth, or time, or even what's natural, hit like, subscribe for more stories from the prehistoric edge of wonder, and leave a comment below. What's your favorite example of nature doing something we thought only humans could do? Your curiosity fuels this channel. Every click, every thought, every echo helps these strange stories keep traveling. Till next time, Keep listening to the echoes.